Hello again. In our previous video, we saw what is called eigenvalues and eigenvectors. And we say that when we write a relation AX is equal to lambda X, the vector X over here is said to be the eigenvector corresponding to the eigenvalue lambda. Now, let's take a look at our eigenvectors over here. So here, the eigenvectors relative to lambda is equal to the set X, which is in Rn, assuming A is Rn, such that Ax is equal to lambda X. Now, there is one more thing, X cannot be equal to 0. Now, let's look at the general behavior of these eigenvectors. If I'm to take two vectors, x1 and then x2, in this set, for the sake of simplicity, let me call it W. If I'm to take two vectors in W, would the sum x1 plus x2 still be in W? As in, if I take two eigenvectors and I add them, would they still be an eigenvector? Well, the only way to find out is to multiply this by A, and to determine whether or not you'll be able to get some lambda multiplying this. Now, because multiplication is distributive for matrices, we can write this as AX1 plus AX2. Now, because x1 and x2 are both eigenvectors, I can write this as lambda x1 plus lambda x2. Hence, I can write this as x1 plus x2. So I have lambda A multiplying x1 plus x2 giving me lambda times x1 plus x2, which is going to imply that x1 plus x2 is going to be in W. Similarly, if I consider a scalar k, and I consider AK times x1, this is going to be k times AX1, which is going to give me k times lambda x1. And I can rewrite this as lambda kx1. Now, because when I multiply by kx, the lambda pops out, it tells me that kx1 is in W. So what this means is that the eigenvectors, the set of eigenvectors are closed under both addition and scalar multiplication. But what's the one thing that it needs to be a subspace? 0. So here, if we consider the set, which is equal to all eigenvectors of lambda, and then we add the 0 element or the 0 vector to it, we get a subspace. And that subspace is what is called the eigenspace of lambda. So let's take a short example. So here, example, let's find the eigenspace of the smallest eigenvalue. given A is equal to 1, 2, 3, 0, 0, 4, 5, 0, 0, 1. Now, to find the eigenspace means I need to find the set of all the eigenvectors of A and include 0 to A. Now, to find, first off, we need to find the eigenvalue. We know that when a matrix is, for triangular matrices, their eigenvectors, their eigenvalues are the diagonal elements. So here, the eigenvalues of A lambda 1 is going to be 1, and then lambda 2 is going to be 4. Now, since it's asking for the eigenspace of the smallest one, we are interested in the eigenspace of lambda is equal to 1. And to do this is to answer the question, how do we find the non-trivial solution of ax minus, a minus lambda I x is equal to 0. Now, doing this quickly, my a minus lambda I is going to give me 1 minus lambda, 2, 3, 0, 4 minus lambda, 5, 0, 0, 1 minus lambda. Now, since I have my lambda to be equal to 1, when I set up the augmented matrix, I'm going to get 0, 2, 3, 0, 3, 5, 0, 0, 0. And don't forget to include the 0 columns since you are solving an augmented matrix. So here, if I'm to find, if I'm to write this in the RREF, I get 0, 1, 0, 0, 0, 1, 0, 0, 0, and then these columns are just going to be zeros. So without loss of generality, if I let this be x1, x2, and x3, I can say that my x3 is equal to 0, my x2 is equal to 0, and I have a free variable over here. So I can let my x1 to be equal to t. Now, looking, since I'm interested in the eigenspace for lambda, which is equal to 1, is going to be t 1, 0, 0, where t is some real number. Now, overall, if I was only interested in the eigenvectors, then it would have been the exact same set, but then the difference will be 0, t cannot be equal to 0. So that is the distinction between the eigenspace and the eigenvectors.